Hi, and welcome to 15.4 Snell's Law. In this lesson, we get to talk about something kind of fun, which is refraction, the refraction of waves, specifically light. So I'm going to talk about really quickly refraction and then a little bit of reflection because number one has to do with that. So here we go. Okay, so let's say you have a light source. In this case, let's use maybe the sun. It's a nice sunny day outside, and you're walking along a path. Maybe you're near a body of water. So here's the water. Well, then the sun's rays, let's say you're over here. Okay, you're standing, you're on the ground, and this is you over here. You're looking at nice sun on water. You know, it's all reflective and like you could see the sun. Yeah, it's pretty cool. So let's make the light ray coming in here. The light is coming into the water here. Now, some of the, like, obviously, one, you could look at the sun. I don't recommend it. But so the sun's rays are going everywhere, right? But let's just pick this one ray. All right. Really, it's just showing the direction of the waves of the electromagnetic wave that comes in. But it strikes the water. Okay. Now, couple things. The first thing is anytime it strikes an interface like this, immediately at this point, you want to draw in your good old buddy, the normal line. But in this case, since the light is going to go through into the next medium, we'll draw the normal line on both sides of the interface between this is air and this is water. So what happens at this interface? Well, some of the light definitely does get reflected. And if you remember, this is our angle of incidence. And then there's an angle of reflection. Oh, this light ray isn't going to meet our eyes. I should have drawn the person up here. And then you could see the reflection of the sunlight in the water. And it's like all sparkly and nice if you were all the way up there. Some of the light rays do, like I said, the direction can change. All right, so this light ray could go like this. Maybe it's something like that. All right, but that angle is too steep to really show the refraction part. So yes, you do get an angle of reflection that is equal to the angle of incidence. But we're going to talk about the angle of refraction. So what happens as it enters the medium? So part of it is reflected, part of it enters the new medium. To know if it bends... Oh boy, what the heck happened here? So to know if it bends towards the normal, that would look like this. So it's bending towards the normal. It's getting this angle smaller. It's bending towards the normal. Or does it perhaps bend away from the normal? So now the angle of refraction is bigger than the angle of incidence. Or if the two mediums have the same optical density, the same index of refraction, if it's the same, the ray's not going to really be refracted at all, and the angle of incidence is equal to the angle of refraction. That's if both indices are the same. But to know what it's going to look like, we have to look at the index of refraction. Now for air, the index of refraction, which we talked about in the last video, is 1, or at least it's very close to 1. So n is equal to 1.00. And see how there's two different mediums? We're going to call this N1 because that's the first medium that the light is in. It's like incident in N1. And N2, we'll call it because there's the second medium there. We need to look at our reference table for the index of refraction of water. So here's on page 2, the indices of refraction. So we said air was very close to 1. And for water, it's 1.33. So N2 is equal to 1.33. By the way, just a reminder, in the word problem, if it says the frequency like that particular 5.09 times 10 to the 14 hertz frequency, that's a hint. Probably, like, let's say they say lucite, and they say this. They're not going to tell you the N is equal to 1.5. They're giving you this hint to say, go to your reference table and pull out this number. They're giving you a hint that there's some hidden information there. Okay, so 1.33, that's what we're dealing with for N2. 1.33. So just in general, if it goes into a more optically dense medium, that means the N is higher. If the N is higher, it bends towards the normal because it's slowing down. That if the N is higher, that means it's going slower. It goes fast through air, but when the light hits water, it slows down and bends towards the normal. If it was the opposite way, then it would be speeding up and it would shoot out, whoa, this way. All right, so sometimes let's say you go from water into air, if you're looking at a fish in the water, and the arrows would go the opposite direction. But that's it. So if the N is higher, it bends towards the normal. If the N is lower, it bends away from the normal. And if the N is the same, it stays the same, like it just continues its straight line of path. What else with this? Okay, so now we have two different ends, and we have two different angles, and Snell's law is all about this. N1, and then sine theta 1 is really sine theta, the incident angle, is equal to N2 sine theta 2, or the refracted angle over here. And it looks a little funky, people get a little tripped up by this. But really, remember, you got 1, 2, 3, 4 unknowns. And here's 1, 2. Those 2 you can normally look up in your reference table. And then 3, 4. They'll either tell you those or you could measure it with a protractor. And then you just plug in the stuff and make sure that your calculator is in degree mode for this because we're using the sine function. All right? And then to solve for theta, don't forget you might have to do like theta is equal to the inverse sine of something. If you're looking for, let's say this is the unknown, then you'll have to eventually do the inverse sine. All right, so it's all coming together here. Let's do the homework. A laser beam is directed at the surface of a smooth, calm pond as represented in the diagram below. Which organisms could be illuminated by the laser light? So the light's coming in. Let's use like green. The light's coming in here. Part of it is going to be reflected, like sun on water. So the bird can be illuminated because part of the light is reflected, but also part of the light goes through the interface and becomes refracted. Now, we're talking about air, which is N is equal to 1, and a calm pond, we can assume it's a pond made of water. So it's going into a more optically dense medium. Well, it's not going to go straight through. We know it's not going to go straight through and hit the seaweed because the ends are different. If the ends were the same, then it would go straight through. Since the N is higher, it bends towards the normal and hits the fish. Bird, fish. The crab would never be illuminated by this laser because that implies that the normal line is some kind of physical thing. The normal line is an invisible line that we use just to measure our angles. But it's not bouncing off. It doesn't bounce off and reflect off the normal line because the normal line's not really there. It's just a way for us to measure our angles. So we're talking bird and fish for number 1. Number 2, a ray of monochromatic yellow light. There it is. So they're giving you a hint that you might have to use that table in the reference table. It passes from water through flint glass and into medium X as shown below. The absolute index of refraction of medium X is, and then they give you a bunch of different information. So the first step I always like to do is figure out what are we talking about here. I see water and flint glass. Let's look at the reference table. Here I see water, so I'm going to write 1.33 on my diagram. And then we have glass, comma, flint. That's flint glass, 1.66. So let's write those two indices in. So it's starting at 1.33, then it goes into 1.66. We'll call this N1, N2, and they want to know what N3 is, question mark, for medium X. Oh my gosh. All right, question mark here. So this diagram makes it look like the line is pretty straight. what I recommend doing is taking a sheet of paper and putting it against the line so you can see if it's bending or not. I'll try to show you what I mean here. So as long as you have some kind of straight edge, even a ruler would be ideal. Like a ruler would be better. If you're rocking with a ruler right now, anything that's a straight edge, that was perfect to use. But I know a lot of people have a piece of paper in front of them because they have their reference table. So you could even use the side of your reference table, as long as it's not all wrinkled up, as a straight edge. And as you can see, I'm having a hard time finding the specific angle, but this is the idea. Oh man. So you want to put the paper or a straight edge, like a ruler, right along the water line right here. And hopefully you see that it actually bends towards the normal as it enters. So this is what it would have been, but now it bends when it hits the flint glass because flint glass has a higher index than water does. Well, what happens when it goes from flint glass into medium X? Is it going to bend towards, bend away, or does it stay the same? This is working out a little bit better, I guess, but not even really, so it's not really showing what I want. If you held a straight edge against this line, hopefully you would see what happens. That the line is completely straight. It doesn't bend anywhere. So if the line is completely straight, that means that N3 has the same index of refraction. There is no bending of the light happening, which means the index is equal to that of flint glass, 1.66. Number 3, a ray of light, there's that frequency in air, is incident at an angle of 40 degrees. So as soon as I see that, I like to also draw in, okay, incident, 40 degrees right there. So that's some hidden information, or it's not even hidden. That's some information there. And it's an air crown glass interface. Okay, so that's just like this line here where the two mediums meet. That's the interface. Shown below. What is the angle of refraction for this light ray? So the index for air, hopefully by now you have it memorized, it's just 1. Well, what's the index for, so that's N1. What's the index for crown glass? All right, here it is, glass, comma, crown. So that's 1.52. So we write that in our diagram. At this point, you could even predict, oh, well, since the index is higher in crown glass, I think it's going to bend towards the normal. And the angle I'm going to solve for, theta 2, or theta r, the refracted angle, is going to be less than 40 degrees. So our prediction is that we're going to solve for an angle, and it's going to be less than 40 degrees. So it says, what's the angle of refraction? We need to do Snell's law, which is N1 sine theta 1 is equal to N2 sine theta 2. Then you plug in the information, and I'm kind of doing the guess method over here because I have all the givens, right? This is theta 1 equals 40. This is the unknown equals question mark. And then we find the equation, substitute. So this is 1 sine theta 1, they tell us, is 40 degrees. Now make sure you're in degree mode in your calculator. N2 is 1.52. And we're looking for sine theta 2. So at this point, you could solve. So I'm going to do 1 times sine 40, which is like 0.6428 if you round it. And that's equal to 1.52 times sine theta 2. Now don't get rid of that in your calculator because we're going to just take that and divide it by 1.52. So don't round it in your calculator. Try not to do any rounding until the end with these. So you just hit divide by 1.52, and you get 0.422, like 9 if you round it. But again, don't round it in your calculator, and like leave it long in your calculator. But you could round it on the paper just to make it easier to write. And that's going to be equal to sine theta 2. So we write sine theta 2. Now, are we done? Is that the angle? So the angle's 0.4229 degrees. We knew it was going to be smaller than 40 degrees, but I didn't think it was going to be that small. What's the last step that we have to do here? Well, the theta 2 isn't by itself yet. And to get theta 2 by itself, we have to do the inverse operation. Just like this was 1.52 times sine, we did the inverse of times, which is divide, to get the variable closer to being by itself. So to get theta 2 by itself, the function here isn't multiply, the function is sine. So we have to do the inverse sine to both sides to get the answer. So this is sine -1, or second sine in your calculator. And then you type in second answer, which I think the second answer is near the negative sign in your calculator. Don't round it like I did. Don't plug this number 0.4229 in your calculator. Use the long decimal that's in your calculator. And you should get an angle of about 25 degrees, or 25.0 something, whatever. We could just call it 25 degrees. And let's compare that to our angle of incidence. So we said we predicted that this angle would be smaller, and it is. It's less than 40. It's 25 degrees. Very nice. Okay, number 4. A light ray traveling in air enters a second medium and its speed slows to 1.71 times 10 to the 8 meters per second. What is the absolute index of refraction of the second medium? So actually, this is kind of a throwback to the previous topic. We're not going to use Snell's law for this one. So this is really reminding you what exactly is the index of refraction. So they're saying it's traveling in air and it enters a second medium, and its new velocity is 1.71 times 10 to the 8 meters per second, and they're looking for the index of refraction. They don't tell you any angles or anything like that, so we cannot use Snell's law because we don't know what the incident angle is or anything like that. But we know what the speed of light in a vacuum is, 10 to the 8 meters per second. So we could just do the definition of the index of refraction. It's just a ratio between the speed of light in a vacuum and the speed of light in the medium that is traveling through. It slows down. Well, this number, tells you, it's a way to measure or describe how much that light slows down. And as you can see, the reason we do that is because it's useful for Snell's law. So you get n is equal to about 1.75, and there's no units for the index of refraction, so that's that. Number 5, a ray of light traveling in air strikes a block of sodium chloride at an angle of incidence of 30 degrees. What is the angle of refraction for the light ray in sodium chloride? Well, I hope they have the index of refraction for sodium chloride. So first of all, we could draw ourselves a little diagram if we want. And here it is. Here's air. That's the incident. Well, we want to show where that angle is, so we draw the normal. The angle of incidence is 30 degrees. So this is theta 1. And it's going into sodium chloride. So we know for air, n is equal to 1. It's on the top of that table. And we want to know what N2 is. We could look that up in our reference table. And then the only other thing that we need to know is this angle, and that's what they're looking for. Okay, so first let's find this for sodium chloride. And here it is, 1.54. So we could write 1.54 here. And now we could write Snell's law. So N1 sine theta 1 is equal to N2 sine theta 2, and they're looking for theta 2. N1 is air. Sine, the first angle they tell you is 30 degrees. That's the incident angle. N2, we looked it up in our reference table, 1.54 for sodium chloride. And you're looking for, again, theta 2, the angle of refraction. So then you just solve. If you want, you could do... is this jumping too many steps? You could divide 1.54, and then you're going to have to do the inverse sine. So you could all just plug it in one step if you really wanted to. Then 1 times sine 30 is just sine 30, but we'll do 1 sine 30 over 1.54, making sure to put it in parentheses when you do that. But I'll do it step by step. But that's an option, because we're going to be doing a lot of these, so the more comfortable you get, the better. Anyway, sine 30 is 0.5. This is 1.54. So we'll divide by 1.54. You get sine theta is equal to a weird decimal, 0.325 if you round it. Don't round it when you do this last step. So you're going to do the inverse sine, second sine, second answer, to get that big long decimal in there. And that's going to be equal to about 18.9 degrees. You could round it to 19 if you want when we're talking degrees. All right, number 6 is the last one. Oh my goodness, this is going to be a long video. All right, number 6. The diagram below shows a ray of light passing from medium X into air. What is the absolute index of refraction of medium X? So now they give you both angles, and they're looking for one of the indices. So we know air is n is equal to 1. But look where it starts. It starts in medium X, and then the second place it goes is the air. So we'll call that N2. All right, so the other thing is it's important to keep, this is N2 and theta 2. This is going to be N1 and theta 1. You want to keep them on the same sides of the equal sign. So you write Snell's law. You substitute in. Now we don't know medium X, and that's where it starts. So we're going to leave that as N1, but that's okay because we know everything else. So again, making sure the 30 stays with the unknown index in your equation. And then you solve. N1 times 0.5, and then 1 times sine 60 is this big, long, weird decimal, so leave that in your calculator. Divide it by 0.5, and you get 1.732, blah, blah, blah. And that's the index of refraction for medium X, the first medium that you were in. And you see how it bends away from the normal? It's higher, 1.73, and then it bends away from the normal because it speeds up and enters a less optically dense medium. Number 7, when a ray of light traveling in water reaches a boundary with air, which is kind of the same situation that we were just in. So water to air, higher index to lower index, it should bend away from the normal. All right, part of the light ray is reflected. So that should be pretty easy to identify, the reflected ray. If you remember, the law of reflection is just the same. And part is refracted. Which ray diagram best represents the paths of the reflected and refracted light rays? Let's eliminate based on the reflected ray. So we want this angle to be the same as the reflected angle. Okay, so that looks good. B looks good. C looks good. D, this is not good. That's bigger than the angle of incidence. So we want the angle of reflection to be the same as the angle of incidence. So we're eliminating D right away just by looking at it. And same with this, we're just going to look at it and see. So if we're going from water into air, a higher index, N1 is equal to 1.33, to a lower index, N2 is equal to 1.00. And I'm doing it like that because it starts here, so that's the first medium. And if it goes into a less optically dense medium, it speeds up and bends away, from the normal. This is looking good to me. And it's definitely not going to reflect back off this imaginary normal line. This interface is a physical thing. It's the boundary between the air and water. This is a made-up dotted line that we as physicists put there just because this particular ray meets at that point. But there's a lot of other rays that are happening, unless it's like a laser. So this was no good. This was definitely no good. We eliminated this because it bends towards the normal. That's not what we want. So it's choice B. Number 8. All right, so which diagram best represents the path taken by a ray of monochromatic light? That just means a single color as it passes from air through the materials shown. So it's kind of the same thing. You have to think about the indices. So it helps to write them out. So this is, it goes from 1. Flint glass, I think, was 1.66. Yep, flint glass is 1.66. Water is 1.33. And air is 1.00 again. So as it goes from air to flint glass, it goes to a more optically dense medium, so it should bend towards. Then as it goes from flint glass to water, it's less optically dense, 1.66, to less optically dense, 1.33, so it should go away. And as it goes from water into air, it's again going to less optically dense, from 1.33 to 1, so it should go away again. This bends towards, so that's good. This bends away, but then this bends towards, so A is not good. And when I say towards, I mean towards the normal. Now, I don't have the normal line drawn at these interfaces, but if it helps, you could draw them, so I'll do that here. So here's the interface here. And this angle looks smaller than that angle to me. So I'm going to say towards. Then if you put like a ruler or a straight edge at this interface right here, it looks like it's slightly bending away. See how if I continue the straight line? All right. It looks like it's bending away here. And it's definitely bending. This is more clear, more pronounced. This angle is bigger than this angle, so it bends away. So far, I'm liking choice B. Let's see if we could eliminate any of these other ones. These are all away, so I could tell right away it's constantly going away like this. And then this, so that's no good. We don't want C. And then this one just looks wonky with the air up here. That's no good. Let's see. So it bends away. Now, see, the first off, it bends away. We want it to bend towards the normal. We want this angle to be smaller than that angle. So that's no good. That was a tricky one. That was a very tricky one. You have to really look at it. So, yep. That's cool. Number 9. A monochromatic light ray traveling in air is incident on the surface of a rectangular block of lucite as shown. So as soon as I see that, I want to look and see what lucite is. I'm curious. So here's lucite, 1.5. We're talking air lucite. That's hidden information right there. So the air is 1. And we said for lucite, it's 1.5. Oh, and it starts in air. So this is N1. And it ends up in lucite. So this is N2. Look at that. Those are some nice numbers that we could use now. It says calculate the angle of refraction of the light ray when it enters the lucite block. Use a protractor to determine the angle of incidence. If you don't have a protractor, assume theta I is equal to 50 degrees. So I wanted you to try to practice measuring the angle because that's protractor skill. It's important for this. Well, it's important for this unit at least. And then we're going to find the angle of refraction. So we'll write Snell's Law. We'll substitute in, making sure that the air matches with the incident, and the lucite matches with the angle of refraction, which is what we're looking for here. So they need to be on the appropriate sides of the equal sign. And we'll solve. So 1 times sine 50 is 0.766, yada, yada, yada. That's equal to that. So you divide by 1.5. Make sure, try to keep it a long decimal in your calculator. And then you get 0.51, blah, 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 sine theta 2. We lost the 2 there. So you have to do the inverse sine again. So theta 2 is equal to second sine, or the inverse sine, second answer, this big long decimal. Don't round it like I did. And you should get 30.7 or 31 degrees. Beautiful. So it bends towards the normal because 30.7 is less than the 50 degrees. In the previous problem, what is the angle of refraction of the light ray as it emerges from the lucite block back into the air? So it's going through the lucite block, and now it's going into the air. So you had to draw that in a little bit. Make yourself a little normal line over here. And now you got to do a little geometry maybe. Or you could probably predict what it is. Shouldn't it be 50? Maybe. Let's prove that. So if you drew the normal line like that, hopefully you see that we have a line that are parallel to each other. So we could do the opposite. What is it? Alternate interior angles. So this is the same. Use that same angle, and I rounded it in my calculator. So if you could do it without rounding in your calculator, and you plug in the big long decimal while you solve, then you'll even get a closer answer to 50 degrees. And so it's going from lucite, which is 1.5. Now it's a different problem. N1 is equal to 1.50. N2, now it's entering the air, and we're looking for, it should bend away from the normal because it's less optically dense. So we're looking for theta 2 now. Theta 1 has now become that 30.7 degrees. So we'll write Snell's Law. Substitute in. Now remember, we're starting in lucite. So this is 1.5. And the angle is that alternate interior angle, which we rounded from our previous answer, 30.7. And try to make it the long one in your calculator if you can. N2 is now air. It's entering air. That's the second medium the light goes to. And then sine, we're looking for theta 2. So when you do the multiplication on the left side, you should get 46.065. And that's equal to 1 times sine theta 2. So divide both sides by 1. The 1 kind of just goes away. That's the nice thing about air. Besides that, it helps you breathe. And then you do theta 2 is the, you find the inverse. Theta 2 is equal to the second answer of the 46.065, blah, 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 blah. So theta 2 is equal to, oops, my bad. I made a mistake. Mr. Nangle, I thought you never made mistakes. I thought you were a perfect person. Well, believe it or not, even I make mistakes sometimes, and I'm not ashamed of my mistakes. No, I might be embarrassed for a split second, but that's totally fine. See what I did? I had to look back. I've been sitting here for like 2 minutes trying to figure out what I did wrong because it gave me an error domain stuff. So what I realized I did eventually was I didn't take the sine of that. I just did 30.7 times 1.5. So make sure you have to do the sine of your answer. So I did sine, second answer, to get that big long decimal in there. And then it gave me 0.51069. And then I multiplied that number, that big long decimal, by 1.5. And you should get 0.766. like that. So this is 0.766, big long number. Then you do second sine, second answer. And I got, look at that, 50 degrees exactly. All right, so that's what we predicted it would be, that this angle is equal to 50 degrees. And there's actually a cool lab that you could do that you use a lucite block and you can make a diagram that looks exactly like this, which is pretty cool. Yep, so people make mistakes. That's okay, though. All right, number 11. An electromagnetic wave of wavelength. Okay, this one is kind of weird. I'm going to have to shift this down a little. So number 11 always throws people for a loop. You really just have to do the guess method and then use an equation that's given to you in your reference table, but I don't really use it too much in the class because we're busy talking about other stuff. The equation that I'm referring to looks like this. It's actually nice that they give you this. It's derived from a combination of this formula. So I spent 15.3 talking about that and what that is. 15.4 is Snell's Law. And, oh, it's actually a combination of this as well. That's where the lambda comes from. But this isn't really showing a new concept. It's to me, it's just showing they're doing the work for you. Just plug in the numbers there. So the way this works is you don't need all three pieces. You could just look at these two pieces, or look at these two pieces and ignore this, or you can ignore this. And I think we're going to end up doing something that looks like this. But the tricky part is that you have to make sure the ones and the twos are on the appropriate side of that fraction. All right, so let's write the given information. They're telling us the wavelength in air. So wavelength 1 is 5.89 times 10 to the negative 7 meters. And the first medium is air, and we know that's 1.00. Then it goes into corn oil, and they're looking for the wavelength. So what's the index for corn oil? It's 1.47. And now we have our given information and our unknown. So we need an equation that has N1, N2, lambda 1, lambda 2, which is in our reference table. So yeah, we're going to make it look like this. Okay. N2 over N1 is equal to lambda 1 over lambda 2. In that order, don't flip those up. So there's our equation right here. We're going to substitute in and solve for lambda 2, which is pretty much 4 times 10 to the negative 7 meters. The way I did that, I just cross-multiplied, and then you basically take this number here divided by 1.47, and you get your answer. All right, so what did we learn today? Mr. Nangle makes mistakes, and everybody makes mistakes, but you got to learn from them, and just don't shy away from things if things seem hard. You got to work the problem. You can do it. All right, have a great day.